The instantaneous rate of change of f at a is equal to the derivative, f prime of a, if it exists. So an example is velocity, like instantaneous velocity of a car. Imagine this. Let's say that we want the instantaneous velocity at time 1 p.m. Consider the average velocity between 1 p.m. and 2 p.m. Basically, let's say it's 1 p.m. right now. I want to know the average velocity of the car in the next hour. Let's say it's 7 miles per hour. I'm driving in a parking lot. Then consider the average velocity in the next minute, from 1 p.m. to 1:01 p.m. The average velocity over the next second, over the next millisecond, over the next microsecond, and so forth. You're approaching, the average velocities here are approaching the instantaneous velocity at 1 p.m. How can you find a derivative? Remember that profit function we had earlier for the widgets? The difference quotient simplified to this. That was the slope of the secant line given the starting value x and given the run h. This gave you the slope of the secant line, the average rate of change. What happens as h approaches 0? We plug in 0 for h and we get this. Negative 2x plus 200. That is a derivative function rule. Just as the derivative of x squared is 2x. Likewise, the derivative of that profit function we had way up here, the derivative of this profit function is given by p prime of x equals negative 2x plus 200. That's a slope function. If you plug in x equals 60, we get $80 per widget. That's the instantaneous rate of change at 60 widgets. So at 60 widgets, the slope of the tangent line, the derivative, is $80 per widget. That's the slope here. Which means that if we're going from 60 widgets to 61 widgets, that means that our profit is increasing by about $80. That was the idea of slope as marginal change. We saw that in 0.14. Well, if you know slopes and points, you can get equations for tangent lines. And there's a principle called local linearity. The idea that if we take a graph, like for example, the graph of y equals the square root of x. If you take a point on the graph, like say 1, 1, zoom in really close, and more, the graph looks like a what? Looks like a line. Anytime you have differentiability, if you zoom in really, really close on the point, the graph's going to look more and more like a line. And you can use linear approximations to approximate the function value for values of x close to 1 here. The tangent line is basically the graph. The tangent line does a really good job of approximating the graph near the point of tangency. Remember, the tangent line only has to go through one point on the graph. So even though we normally talk about two distinct points determining a line, a tangent line only has to go through one point on the graph. But it's a limiting process. We let the second point approach the first point. Secant lines approach the tangent line. Again, if the run is 1, the rise is the slope. The derivative is an approximation. So for example, if we produce one more widget, the profit increases by about $80, the derivative. The derivative was $80 per widget. P prime of 60 was $80 per widget. Graphing. If you have a derivative function, hey, if you know where the derivative is positive, if you know where the derivative is negative, if you know where the derivative is, what's the slope of this tangent line? 0, that can help you graph functions. And we're especially interested in max points and min points. Max points and min points. And that's where the derivative is either 0 or undefined. For absolute value, at this point here, the derivative is undefined. All right, that was a preview of derivatives. You're going to use them to graph functions and much more. To find out where you can get local max or min points, you set the derivative equal to 0 or see where it's undefined. In calculus, you'll learn much more about derivatives.